Okay, this is part number 5, Dr. Emanuel's lecture number 24, part 5, Divergence and Curl. So finally we're getting to the conclusion of this semester and the conclusion of this 5th video. Okay, so here we're going to just summarize to try to get everything together. We have covered a lot of material. So we just want to make sure that you can follow and keep it separate. Okay, so the first thing I like to do is just talk about simple derivatives. Okay, just a very simple derivative. They're just usually a vector, and it keeps it a vector. Okay, as an example, we're taking the partial with respect to x of this specific function. Notice, we are taking the what? The function, we're taking the partial as it respects to one variable, x. We're not doing x, y, z. When we did that with cross product, we did x, y, z. We're not doing x, y, z. We're doing just x. So that's a simple derivative. As you can see, you're not changing the direction of any of them. Taking the partial as it respects to x, and you're trying to find out at what angle, because that's basically all it is what angle are you being tangential to each of those components, okay, or perpendicular, we call it. Okay, so what else have we discovered? Okay, we figured out what a gradient is, okay? We found out that a gradient, okay, this is how we define a gradient, and as you can see, a gradient is not taking a simple derivative, it is taking a partial of each of the components of the derivative. Okay? So you're taking a partial of each one of these. And you're starting with a what? This is nothing but a function. It doesn't have any direction. It's not a vector. So you're taking a scalar, you're taking the partials in respect of each of the components, x, y, and z. Okay? And we have the same phi is used for all of them. The same phi is used for all of them in our derivatives. So we're going from a scalar to a what? A vector. Get that? From a scalar to a vector, that's what a gradient does. Okay, simple derivative just keeps it a vector. Okay, now we have divergence. Okay, and with our divergence, we have the same thing here. We're taking what? The partial of each of the components in respect to its own variable. Okay? So the x is with the x, the f of x with the y, the z with the z. Okay? The components of the x of f in derivative. Now this is taking a vector and converting this vector right here, our f vector, into a what? Scalar. Components of f is what is used for the derivative. For the gradient, you're taking all of them. You're not separating them. Here, you're separating them. And you're taking each component separately. That's not what you're doing with a gradient. You're taking the entire function and you're taking the derivative of all of them. So what happens with the curl? So with the curl, we're taking the cross product. Okay? Here we were taking like the dot product, the cross product, and here we just no product. This is just called the gradient. Okay? So this takes a vector and it keeps it a vector. Doesn't change it at all. So clearly remember there's 4 different types of vector derivatives. Simple derivatives, keep it a vector, which matches with your curl, but that's for cross product. And you have your gradient will convert a scalar to a vector, and a divergence is going to convert a vector to a scalar. Okay, and we saw that we've been able to cross them. We've been able to use this twice to cross. So that with omega. We saw that we was able to use also our gradient, and we were able to multiply our gradient. We was able to cross that with the results from our curl. Okay, so we're able to now use these together. Summary of notes. Okay, things you need to know. Note that we have here, if you're going to take a partial of 2 different derivatives on the same function, the different partials in respect to x and partial with respect to y on the same function, you can write it this way, and then you can write it, the functions itself, the entire function, just like we did for what? For the gradient. Okay. So you can see that here. Now, what else happens here? Now, when we perform this function, you're taking the f of x and the f of y, and you're taking both with respect to x, and you're taking your z with respect to x. Okay, so it could be 3 components, but you're only going to cough up with 2 of them because you're only taking a partial with respect to 2 of them. Then you take the partial with respect to y, reference to f of x, f of y, f of z, in each of its components. Then when you come down, you can combine all the I components together, and all the j components together, and all your k components together. And you have a real neat thing. Okay? Now look here, when we look at the, what do we call it? The divergence. Okay, the dot is the divergence. The gradient vector is not a dot product. Be careful. The gradient is not a dot product. So these are things that you'll slip into, that you might fall. So we're here to remind you and help you realize. And as you can see here, the divergence, okay, and then we see this is the works as an operation as a cross product. So now we will let you do some practice problems. Yes, it's your turn now. Find the curl of the vector field. Look at it. It's just coming out and turning all over the place. You love it. Okay? You have practice problem number 3, practice problem number 4. Remember we talked about the B field? See, there's the B field. There's our joule. There's our permittivity constant. Okay, so now we're getting a lot of different things here. Okay, excellent. Okay, and here you'll be taking the surface, and then you'll be taking the volume. And as you can see here you did it again. You have your normal vector times your curl. Okay, that's your curl. All right, I appreciate it. Thank you for being part of our study, and may you enjoy this study.